My dear student, colleagues, and all the viewers who are watching this program live from Facebook page and YouTube channel, I'd like to welcome you all to our International Physics webinar, and I'm happy to share with you all that today is our 76th International Physics webinar, and very good afternoon to all. For those who are watching this program live from Bangladesh, and very good morning to all those who are watching this program from UK. Hope you are well and safe from corona pandemic. All we know that we are staying in a corona pandemic situation. We cannot continue our normal academic program inside the campus due to the corona pandemic. So we are trying to adjust with this new normal situation, and we have to start our online program to continue our academic program. So I think you have already come to know that our Department of Physics, Pabna University of Science and Technology, have already started its online program, including online classes and online international physics webinar. So, and we have successfully completed our 75th International Physics webinar, and today is our 76th International Physics webinar. And today is a very important day for our department. Today, I'd like to welcome you all to a joint session between Department of Physics, Pabna University of Science and Technology, and Sorbonne University and Albert Einstein Center, ITP University of Bern, Switzerland, in high energy physics. And we have with us here today Dr. Ignatios Antoniadis, Director of Research, LPTHE, CNRS, and Sorbonne University Paris Fund, and Albert Einstein Center, ITP University of Bern, Switzerland, connecting with us from UK. So he has already connected with us. I'd like to welcome our speaker. So, sir, good morning and good afternoon here. So, welcome to our International Physics webinar, and thanks for accepting our invitation, sir.
Good morning. Thank you for the invitation and for the chance.
It's our pleasure, sir, and it's my honor to and privilege to host you in my International Physics webinar. So for those who are new, I'd like to inform that we have divided our webinar in three parts. First, we would like to introduce our speaker with all of you, and then our speaker will deliver his speech, and at the end, we have a discussion session. In that time, anybody can join with us, and you can ask question by commenting also. So I think you have already come to know the title of today's International Physics webinar. Title is Challenges in Particle Physics and Cosmology, and our speaker is Dr. Ignatios Antoniadis. He's currently working as a Director of Research, LPTHE, CNRS, and Sorbonne University Paris Fund, and Albert Einstein Center, ITP, University of Bern, Switzerland. So he's a Greek physicist who mainly studied and worked in France. He is known to be one of the world's specialists in string theory. He's currently working on the latter and therefore on supersymmetry, but also on quantum gravity at CERN in Geneva. He's a permanent member of the theory division of CERN in Geneva. His research concerns a vast field of theoretical elementary particle physics, and he obtained a silver medal from the CNRS, National Center for Scientific Research, in particular thanks to his work on the theory of superstrings. He had a very important role, especially regarding the construction of four-dimensional string theories. The surprising consequence of these theories could lead to a change in the gravitational forces over short distances and to the appearance of additional spatial dimension at the microscopic scale. He wrote an article summarizing this for a magazine in 2001, which also featured Brian Greene, another great specialist in string theory. We can see his research areas: string theory, quantum gravity, supersymmetric theory, grand unified theory. He played an important role in the development of superstring theory models in 4 dimension fermionic construction. He is particularly known for investigating the phenomenology of superstring theory. That is, for example, great unified theories derived their form at low energies and a statement about the particle spectrum, and possibly observable effects such as extra dimension and change the gravitational force at short distances. His professional training, you can see his professional training from 1977 to 2002, and we can see his research gate ID. His research gate point is 46.61. So thanks all for all of your patience. Now it's time to go to our speaker. So I'd like to welcome you again, sir, to our International Physics webinar. It's your time, so you can start your session.
So thank you very much, Dr. Kumar, for the invitation, for the introduction. So my talk today will be to give you a flavor about some current topics of particle physics and cosmology. So let me go to full screen. Is it okay? Can you see?
Yes, sir. Okay, it's okay. You can see.
Yeah. So the challenge of fundamental theory of nature would be to describe physics at all scales, starting from very small scales, which is the topic of the area of particle physics, and to very large scales, which is the subject of cosmology. So on the left, the picture is from CERN, from Geneva, Geneva Lake, where there is the LHC experiment there, where there are proton colliders. And on the right, we have a picture of the universe as seen by the Planck satellite. I'd say a few words since I don't see you, I'm not sure what is, I guess there are students, so I don't know what is exactly your background, so please excuse me if there are some things you know, some others it may be more advanced. So we'll start with just a short review on particle physics that studies phenomena at very short distances. And the aim is to find the structure of matter and how it interacts with fundamental forces. The experimental tools are particle accelerators, which can be thought as microscopes of today times. In particular, this is another picture of the Large Hadron Collider at CERN in Geneva, which is the world's more powerful microscope at this time. And this is a view of the two main experiments that search for study the matter at very short distances and search for new phenomena. And in particular, they have discovered the so-called Higgs particle in 2013. So that's already some years ago. So this is ATLAS and this is CMS. ATLAS is in Switzerland, CMS is in France. And about 100 kilometers, 100 meters, down to in the Earth. And the tunnel has about 27 kilometers circumference. We already discussed, the community of particle physics, new experiments. And one possibility which is discussed is to have a new collider much bigger than the previous one, with a circumference of about 100 kilometers that go around here, as you see. This small circle is the LHC. This is Geneva Lake. So in principle, this the new tunnel would go under the lake and go around here. Inside this red boundary is Switzerland, and outside is France. There are other programs of this type that are discussed, like in China. Okay, so that is the current status of particle physics. Then, on the other hand, we have cosmology, which studies phenomena at very large distances, with the aim to learn about the evolution of the universe at very early times, just after the Big Bang. And in particular, they measure. There are experiments that measure the temperature fluctuations in the sky. So this is a picture of the Planck satellite, which was launched many years ago, and now it stopped, and studied the fluctuations of around the cosmic microwave background and the anisotropies, and gave rise in particular this picture that they showed you here, this one. As in the case of particle physics, in cosmology also there is a lot of discussion about the future, and this is a picture of a future experiment satellite, another satellite, which is called Euclid, and will be the mission of the European Space Agency that has been approved. Although it appears that these two branches of physics study different phenomena, because one studies very short distances while the other studies very large distances, it turns out that both observations, both ways of studying physics, they study the same law. And the reason is that if we look very far in the sky, then we take pictures of how the universe was many, many years ago, at the time that it was very small, very hot, and at that time it was governed by the laws of particle physics. So at the end, we learn the same physics, but studying different phenomena, either at very short distances or at very large distances. That precisely is one of the pictures maybe you have seen elsewhere, which says, which is just picture of the evolution of the universe, which has an age of about 14 billion years. And at very early time, when the universe was very small, the law of physics are the same that we study now in particle colliders. So when we look at pictures in the sky that come from very far, we just take pictures of this period, very the time of the universe. So let me now go a bit on the theory. The phenomena, the current phenomena of particle physics can be described very accurately by the so-called standard model, which describes the strong, weak, and electromagnetic interactions. And this is the mathematical tool is a quantum field theory that unifies quantum mechanics with special relativity. And it is based on a symmetry principle, which is called gauge invariance, and which is based on this gauge group. So this theory, standard theory, has 17 parameters, and it provides a very accurate description of all phenomena that we measure, in particular at LHC, at present energies. It contains 3 sectors, which are describe the constituents of matter as we know right now. One sector contains the mediators of the interactions, of the 3 interactions, of the 3 forces, which are the photon, the W and Z of the electroweak forces, and the gluons of the strong interactions. Then we have the matter, which are composed by the 3 generations of quark and leptons that we made on off. Actually, we're made off only of 1 generation, but still the others are there. They have been discovered. And then there is a third sector that was discovered in 2013, and which contains a scalar particle, which is called Higgs particle, and is responsible for the breaking, as we say, of the electroweak symmetry, and for providing masses to elementary masses, to the elementary particles of quark and leptons. This theory has been tested very accurately. This is a picture from a common analysis between the two experiments, the ATLAS and the CMS, that gave rise to a paper with 5,000 authors already for years now. And in particular, it studies the Higgs discovery, and this is the accuracy of the mass. And these measurements here are measurements of various parameters, observables, that are described very accurately by the standard model, which is the prediction here in the dashed line. And as I said, the discovery of Higgs particles gave a Nobel Prize in 2013 to Francois Englert and Peter Higgs for the discovery. Then we have the theory, a model for cosmology, for the evolution of the universe, which is called also a standard model of cosmology, under the symbol of lambda CDM. So lambda is the cosmological constant that we'll talk a bit later. CDM is called dark matter. And these are actually the contents, some of the main contents of the universe, which are needed for this theory to describe the observations. So the temperature fluctuations can be plotted in this picture as a function of the angular scale in the sky, and take a Fourier transform, and then one takes this figure. The continuous line is the prediction of the theory, and the red dots are the observations. You see, there is a very accurate description, again, the theoretical description of what we observe in the sky. James Peebles was one of the inventors of this analysis in the theory, and shared the Nobel Prize last year together with two other astrophysicists on exoplanets. So I'll take an example of a common research right now, both from the point of view of using both observations in the universe and also in particle physics. And this has to do with the content of the universe. And I said it seems from the standard model of cosmology that the universe is made up of substances that have not been observed. And indeed, the ordinary matter, which is, as I said, which is composed by quark and leptons, it seems to be only a tiny fraction of the matter of the universe, less than 5%, while there is a non-luminous dark matter, in other words, matter that does not give rise to light, but we feel it gravitationally from the observations. And this dark matter should describe around 1/4 of the content of the universe. The other three quarters are due to another substance that still is unknown to us, which is called dark energy, and I will come back later. I mean, one of the possibilities to describe dark matter is that it is due to some particle which is stable for the time scales of the universe, and which that is not part of the particles of the Standard Model. And in that case, it could be observed either by experiments in particle physics or by experiments in astroparticle experiments, depending, of course, what is the mass and the interactions of this new particle. This is one possibility. So this asserts that is where we put together sets of new particles that could describe the dark matter from particle physics experiments. So these are the blue band is the exclusion line of present from the LHC, and the yellow bands are searches that can be done after the LHC update in the future using the high luminosity, or of course in future experiments. And the various curves here correspond to exclusion plots searching for dark matter from astroparticle experiments. So now going to a bit further, then ultimately would like to find a theory that could describe at this physics at all scales, from short distances to very large distances. So such a theory immediately faces a problem, which is how precisely to describe different phenomena which appear in different scales. And here I list some of the main scales that appear, that we know how physics appears from observations. So on one hand, we have a scale here which is called quantum gravity, which is a Planck scale, which is so this is in the scale here is energy. So as we go higher in energies, it means short in distances by the uncertainty principle. So this scale is a quantum gravity scale where gravity becomes strong, and it's a very high scale, it's a Planck scale. Somewhere here we have the scale of electroweak interactions of the Standard Model, which where there are indications that there is theoretical, mostly indications that there may be new physics around that scale in order to describe, in order to be able to answer to questions which are left unanswered from the Standard Model. And in particular, it could be also a dark matter particle that that could have a mass which is around the TeV scale, and interactions with the same strength as the electroweak interactions, which is an interesting possibility that it is explored, although for the moment there are negative results. Now, a possible extension of the Standard Model that solves some of the questions, theoretical mainly questions, that poses is the supersymmetry. Supersymmetry is a symmetry, is a hypothetical symmetry, which is a new type of symmetry, that relates particles with different spins. So with spins which differ by half. So in other words, between bosons and fermions. It is a well-motivated proposal which addresses, as I said, several open problems of the Standard Model. And in particular, it has several consequences that I list here, which support the possibility of that this symmetry is a symmetry of nature. So the first consequence is that predicts the existence of elementary scalars, because there are elementary fermions, which are the quarks and leptons. And indeed, the first elementary scalar that has been observed was the Higgs particle. Then it allows to realize the unification of the three forces of the Standard Model when you extrapolate them at very large distances, at very large energies, at high energies. It appears that all forces unify at the same scale, assuming that there is supersymmetry not far from the electroweak scales. It also contains a candidate for dark matter, which is the lightest supersymmetric particle, and which is stable and has the right mass and interactions to describe the dark matter. It also addresses theoretical problems like the so-called hierarchy problem. There was the stability of the Higgs of the mass of the Higgs particle from radiative corrections of high energy theory, whatever this is, including gravity. It also predicts the existence of a light Higgs particle with a mass less than 130 GeV, and this is compatible with the present discovery of the Higgs particle, which has a mass 125 GeV. And also it has another nice behavior as theoretical behavior at high energies. It improves the ultraviolet behavior of the theory, and it also it's an important ingredient of another theory which is called string theory, which is a candidate of quantum gravity. Right now, there is no experimental indication of supersymmetry. There are bounds. This is a typical graph with bounds from various processes in Atlas. And this line corresponds to 1 TeV. And roughly all these bounds say that supersymmetry is excluded, supersymmetric particles are excluded up to around that scale. However, I would like to say that in addition to supersymmetry, experimentally, we don't have right now indication of any other physics beyond also supersymmetry, beyond the Standard Model. And these are various searches of different theories and proposals with names like extra dimensions, new gauge bosons, heavy quarks, exotic fermions, excited fermions, and so on. Here again, this line corresponds to 1 TeV, and this is 10 TeV. So you see also alternative theories to supersymmetry that extend the Standard Model, theoretical models. Right now, there are just exclusion curves, and we don't have any indication that they are there. However, for many reasons, mainly theoretical, physics community believes that supersymmetries should be there at some more fundamental level, but we don't know at what scale. But there are several theoretical arguments towards supporting supersymmetry. So this is one scale here, which is, that's why I didn't put different, I put together with electroweak interactions around the TV scale. Then we have another scale is the scale associated to dark energy, which, as I thought before, it constitutes about 3/4 of the content of the universe. And the simplest explanation of the dark energy is an extra term in the Einstein equations, which is called cosmological constant. But this cosmological constant must be very small. Let me sorry to go here to say a few words. A cosmological constant describes, a constant in the Einstein equations, and has, if we put it on the other side together with the matter, then one can also alternatively describe it as a new substance of matter, which has an equation of state of a negative pressure equal to in absolute value with the energy density. And this energy density is precisely lambda over g, where g is the Newton constant. Now, view it as a constant in the equations of motion. It has a classical size, a classical length of length to the -2, like the curvature. And this length can be deduced from observations. Essentially, is related to the size of the observable universe. And we can obtain an estimate from the measurement of the Hubble parameter, and which is when we put the numbers, we find around 10 to the 26 meters. So this is more or less the size of the observable universe. On the other hand, if we understand it as a dark energy, as a substance, as an energy on the other side of the equation of motion, then the relevant scale to the energy is lambda over g. Now, the lambda over g does not define the length classically, but it can define a length quantum mechanically using the Planck constant, h bar, and the speed of light. And this, and then one finds a length to the -4, where this length is much different than the classical one. It is, we can call it dark energy length, and it is very different to this one. It's about 85 micrometers. It is interesting that this range of lengths is a range where the smallest range where Newton's law has been studied in the laboratory. This is a picture of the latest experiment, which is already quite old now, 2006, which is an Eötvös type experiment. So it's a sophisticated pendulum that studies gravity at short distances, or in general new forces at short distances, and in particular measured the Newton's law valid to around 50 micrometers, which is of the same order as the dark energy length. Right now, the results are negative. There's no indication of any new force at short distances, but this is an interesting coincidence. So this is the reason that I have put here as a scale, the dark energy scale, milli electron volt, which corresponds to the 100 micrometers in length. And in this picture, it is interesting that the electroweak scale sits somewhere in the middle between the geometric middle, between the in a logarithmic scale, of course, between dark energy and length and quantum gravity scale. Then another interesting scale that has to do with the early evolution of the universe is what is called scale of inflation. So it appears that the phenomena support that our universe had a period of accelerated expansion, much faster than today, which could be driven by a cosmological constant, which is much bigger in magnitude than the cosmological constant of today. And an empty universe with such a big cosmological constant, it is called De Sitter universe. So let me go back and go here and say a few words about the De Sitter spacetime. So the De Sitter spacetime would be an empty universe that contains no matter, and it is a solution of Einstein equations in the presence of a positive cosmological constant. This space is this space-time is very similar from the symmetry point of view to the flat space-time, in the sense that it has 10 isometries, which are the same number as the isometries of flat space. The isometries of flat space are describe a Poincaré group, which contains 4 translations, 3 rotations, and 3 Lorentz boosts. The 10 isometries of the Sitter spacetime form a different group, which is a non-compact version of SO5, is SO4,1. It can be described like a sphere, a non-compact sphere, because of this. So a sphere is the simplest way to obtain it is by going to one extra dimension and put a constraint that the coordinate square is equal to the radius square. So here the coordinate is non-compact. Therefore, by putting an extra constraint, we added an extra fifth dimension and we put a constraint. Then we form a hyperboloid, 4-dimensional hyperboloid, which is the Sitter space. H is called, it's a Hubble constant, which is a constant in the Sitter space, and it is related to the curvature invariant and to the cosmological constant by this relation. Because of the maximal symmetry, all the curvature invariants characterized by the Riemann tensor are given in terms of just one quantity, which is the Hubble constant. This space looks like this, this yellow pixel. So is the surface that you can see here, where the horizontal, so the vertical line corresponds to the time direction, and the so the vertical line corresponds to the time direction, and the horizontal line corresponds to space, where of course space is 3-dimensional. There are several ways to parameterize this space. For cosmology, the relevant way, the most important way is to cut the space by half in this along this black line, and then one can find the coordinates, time-dependent coordinates, which describe an expanding universe. and with a scale factor which depends exponentially on time. So given by where h is the Hubble constant. That's why it's called also Hubble constant. Here one can also follow which are the 10 isometries, because we have already the 3 rotations of space, the three translations of space. Then we have a scale transformation in which the space coordinates are rescaled by some quantity, and this rescale is compensated by a time translation. And similarly, there are three more transformations, which are called special conformal transformations, that complete this group. As I said, in cosmological coordinate system, we cannot cover the full space. I mean, in the flat coordinates, but we can do another slicing which cover the full space, and this can be easily understood from this picture. Is we have at a given time, so time is vertical, and at a given time we have spheres, three spheres that expand. First of all, in the past it was contracted. They go to some minimal size. And then they expand. So you have this parametrization where d omega 3 is the unit sphere, and instead of exponential, we have the cosine dependence. Now, as I mentioned, this space, this de Sitter space, was introduced it was motivated by physical reasons to explain some of the problems of the observable universe, and some of the questions is why the universe looks homogeneous and isotropic from everywhere one looks. In any direction one looks in the sky. One obvious explanation would be that all the regions in the sky were causally connected in the past, were communicated in the past. However, if we make this hypothesis and we extrapolate the present universe, the size of the present universe, by using the Einstein equations, using the present content of the universe, then one finds that the observable universe actually is very big, and it is made up of a huge number of causally disconnected regions. So that is the problem. That was a problem. And the possible proposal that provides an answer, which is very simple, to provide an answer to this question, is to postulate that the universe had a period of expansion which was much faster than today, and in particular exponential expansion, and therefore it was a small region in the past which was causally connected, had an exponential expansion, became very big, and then the evolution changed, became slower, and gave rise to the universe today. So this can explain the homogeneity, the isotropy, and the flatness problems that I explained before. Now, with an exponential expansion, for this to work, one needs approximately 50 to 60 e-foldings in the exponent of expansion in order to make the universe as large as it is today. So that is the reason why the Sitter space and cosmological constant was introduced. And subsequently, it was shown that actually small isotropies from this slight deviation of the de Sitter space could give rise to quantum fluctuations that later on could involve and give rise to the galaxies that we see together today. So this picture can give a prediction for the density fluctuations, which are compatible with this picture that we see today. And this is the lambda CDM model that assumes, okay, also that today there is another cosmological constant, but much smaller than in the past during inflation. So the inflation is a theoretical paradigm, a theoretical model, which is consistent with cosmological observations. But of course, it's a phenomenological model. In other words, there is no real theory as the standard model of particle physics. A way to describe it is by postulating that the existence of a new scalar field that drives the universe expansion at very early times. Now, new scalar field, now we know that scalar fields exist, like the Higgs field. So in principle, there could be also another one which describes the inflation. And the idea is that the potential, the scalar potential, which is of the inflaton, has a region which is very flat, and then it goes down to some minimum. So this flat region could describe precisely a region where the potential is almost constant, and therefore there is a cosmological constant, and this cosmological constant describes, gives rise to an exponential expansion of the universe that could describe the inflation. From the name, it comes from there. And then there's this scalar field, which is called inflaton. It continues to slow down to the potential. In that region, the inflation stops because the potential is not anymore constant. And then eventually it goes down to the present, to the minimum, which describes the present state of the universe. So this region of inflation is characterized can be characterized by a region where the first and the second derivative here is small compared to the de Sitter curvature, in other words, to the height of the potential. So yeah, so I'm back here, and to the scales, where I just described various scales that they enter and what type of theories we have to explain them. And now I would like to come back and ask the question, is there a way then for a fundamental theory to explain at the same time the physics at every such different scale? Now, before going to there, let me say a few words about the string theory. String theory is a theory that it's a candidate of quantum gravity. In other words, a theory that could put together the general relativity with quantum mechanics. At the cost of introducing new elementary structure of matter, which are strings instead of point particles. There has been a lot of I mean, string theory is already around many years, and obviously there have been a lot of studies of how to implement the cosmological model that I described before within string theory. It turns out that the problem of vacuum energy and the description of inflation within string theory is related to another problem within string theory, which is called module stabilization. This has to do with the following fact, that the string theory is defined in 10 dimensions, superstring theories actually in 10 or 11 dimensions, where it appears to be mainly unique. It doesn't have parameters other than a mass scale, which is related to the string scale, or a length which is related to the string length. However, one has to get rid of the extra dimensions and go to 4 dimensions, and this requires mathematically a process of what is called compactification. In practice, it means that one takes the extra dimensions and one considers them as small, compact. If it is just one, then it is relatively simple to understand. Is to make a circle or element or a line element. However, if you have several extra dimensions, then this compact space could be much more complicated and could parameterize a compactification manifold, which has parameters that parameterize the sizes and the shapes of this manifold, cycles, shapes, and so on. It turns out that these parameters are actually expectation values of scalar fields that exist upon compactification, and bring a problem, which is a problem of how to fix these parameters, and whether by fixing these parameters one can describe the natural. Now, assuming that the theory is supersymmetric, these parameters become complex, and they enter in the determination of the couplings of the low energy theory, and they are called moduli. So if the moduli are massless, and then obviously the theory would be inconsistent, because the moduli would give rise to extra long-range forces like gravity. They could be produced cosmologically, could be seen in accelerators, and all these are in contradiction with present observations. So an outstanding problem is that one has to provide to this moduli a potential and stabilize them and make them massive at some values. And at these values, one could determine the parameters of the effective field theory, in particular the masses and the couplings of the standard model, if one can embed it within string theory. So this is the name, the source of the name of under moduli stabilization. With the modular stabilization, avoid the experimental conflict and fix the vacuum expectation values of the fields by computing the low energy couplings. Now, this stabilization can be done by generating a potential for these fields, a moduli potential, and can be done either in a way that preserves supersymmetry or in a way that breaks supersymmetry. And these effects could be either non-perturbative in nature, in other words, with a strong coupling, or it can be based on turning on some new parameters, which are called fluxes, and which are generalizations of magnetic fields. This is it has been realized that there is a way that there are discrete parameters in the theory which have to do with the existence of these fluxes, and which, as I said, these fluxes are generalization of magnetic fields. Instead of the Gates fields, we have higher rank tensors which exist in string theory, and this generalized Gates fields could have magnetic fluxes which are quantized, and then in the presence of these fluxes one can generate a potential and one can fix the moduli. Now in this process one could try to, there have been a lot of studies of trying to find vacua after fixing the moduli, which are not flat, but they are de Sitter, that they have a positive cosmological constant. It turns out that this is a difficult problem, and the difficulties finally led to a conjecture that either forbids the Sitter minima or they forbid standard slow roll inflation. This conjecture is written as conditions on the first and the second derivative of the potential, one or the other. And one can think of them as constraining precisely a flat region of the potential. Flat in the sense that the first and the second derivatives of the potential should be small. There is right now a debate on the validity of this conjecture, because the validity of this conjecture depends on the arguments, on the assumptions, which are, there is no proof, but there are heuristic arguments based on classical string theory without by ignoring quantum corrections. So this is just to give you the picture of how the research is going on also in the context of string theory to find the Sitter solutions that could describe either the present universe or a past exponentially expanding inflationary universe. So going back now to the problem of scales, an interesting question is whether there are connections and whether precisely the physics associated to these scales that I described before is connected. There are connections. So I was planning to describe a proposal for a direct connection between the inflation scale and the supersymmetry breaking scale, which is I motivated before. But I think I don't have much time, so I will just say a few words, and then I will go to the conclusions. I'll stop. So this direct connection is by identifying the inflaton field, which is a scalar particle, with the superpartner under supersymmetry, with what is called Goldstino, which is the Goldstone fermion of spontaneous supersymmetry breaking. Supersymmetry is like any other symmetry, which when it is global and it is broken spontaneously, in other words, if the vacuum is not invariant at the symmetry, then it predicts the existence of a particle which is called Goldstone particle. It's a massless particle, and for the fermion, because for supersymmetry, because the supersymmetry is a symmetry between bosons and fermions, the Goldstone particle should be a fermion, like the quark and lepton, should have a spin 1/2. This particle should be zero, should be zero mass, and if supersymmetry is a global symmetry. Now, in the presence of gravity, it turns out that the supersymmetry becomes a local symmetry, and because there is also a superpartner of the graviton, and this superpartner of the graviton has spin 3/2, and it is called gravitino. If supersymmetry is spontaneously broken, then we have an analog of the Higgs phenomenon, of what happens in the Higgs phenomenon of the Standard Model. Now we have discovered the Higgs particle. And the analog phenomenon here is that the Goldstone fermion of spontaneous supersymmetry breaking, is absorbed by the gravitino, the spin 3/2 mediator of local supersymmetry, and becomes massive in the same way that the W and Z of electroweak interactions become massive by absorbing the would-be Goldstone bosons of the breaking of the electroweak symmetry. So the postulate here is that this Goldstone fermion of supersymmetry breaking is precisely the partner of the inflaton. This makes a direct correction between inflation and supersymmetry, which has interesting consequences, phenomenological consequences, and predictions which I don't have time to describe, and also they may require more technical presentation. I have left in my transparencies in case, I don't know if you put them on the web later on, but you can look at them and if you have questions, you may ask, contact me by email later on. So I switch now to my conclusions. As I said, I talked about some overview of present challenges in fundamental fields of particle physics and cosmology. And in particular, I talked about the origin of the different scales. They're all the breaking scale of supersymmetry in nature, the origin of inflation and the nature of the inflaton field, and the nature of dark energy. And finally, I just mentioned that there is a general class of models and a proposal that could connect inflation with supersymmetry breaking and identify the nature of the inflaton field. So thank you very much.
Thank you, sir, for your wonderful presentation. And I think students have learned a lot of things in string theory and high-energy physics. So if you allow us, we can start our discussion session. We have got some question in comment section. So the first question, so is dark energy interact with neutrinos only? And is graviton interact with dark matter?
It depends on the nature of dark energy. If it is a cosmological constant, no, it's unrelated to neutrinos, and it is unrelated to dark matter. However, there are models where the dark energy is not is not a constant, is not a cosmological constant, but it is a time-dependent constant due to an extra scalar field, which is called quintessence field, and in which case one can have models of dark energy, of quintessence dark energy, which couple to dark matter in a non-trivial way, and even to neutrinos.
Thank you, sir. So is universe really infinite or just
can you repeat
really
what
big?
you said?
So is the universe really infinite or just really big?
well, our present observations say that the universe is finite. It has a size, at least the observable part is 10 to the 26 meters. But of course, we don't know.
Thank you, sir. So we have another question. So are galaxies really moving away from us, just expanding?
There has been established that independently of the local velocities of galaxies, there is a common velocity which is due to the expansion of the universe, and this expansion of the universe is measured in terms of the Hubble constant. And there have been a lot of measurements of different ways of this Hubble constant, which measures the expansion. There has been recently some inconsistencies between various experiments, but these inconsistencies had to do with expansions between comparison between short and large length scales.
Thank you, sir. So there is another question. So is there a relationship between cosmological constant and dark energy?
Yes, that's what I said, that the simplest explanation of the dark energy would be just a cosmological constant, which can be rephrased as a fluid, so as a substance of energy that has also a pressure equal in magnitude and negative with the energy.
Thank you, sir. We have another question, sir. Recently, you have worked on magnetic deformation of supermaxwell theory in supergravity. Can you tell about
Can you repeat that
in
question?
brief?
What did you say?
So, sir, recently you have worked on magnetic deformation of supermaxwell theory in supergravity. So, can you tell about that in
it's
brief?
very technical now to answer, because my talk didn't refer at all to this.
I understand. Okay. So, thank you. So, hopefully, in near future, we'll arrange another webinar on that field. So, if you agree. So, we have another question. So, what are the possible candidates for inflation in string theory?
There are several models based on the effective field theory, which essentially they predict it's a model of the inflaton with particular potential. The main, the present debate is whether all these models that have been worked out can be really derived from string theory, or they contain assumptions that, for instance, had to do with these difficulties to obtain the super vacuum in string theory. So there, I would say the short answer is no. There is no real derivation of inflation from string theory, but there are proposals and models, and the research is going on.
Great. So thank you, sir. We have another question. So will you discuss briefly about the large-scale scenarios and fiber inflation model?
Large-scale scenarios and?
Yeah.
Oh,
and the fiber inflation.
By large scale means that the inflaton takes fluctuations of the inflatons take values which are bigger than the Planck scale, and there is a debate since the inflation picture with a scalar field is an effective description. If one considers fluctuations which are bigger than the Planck scales, then maybe the approximation breaks down. There is again an ongoing discussion. I don't think I can be more technical at this moment. more precise.
So thank you, sir. Yeah. So we have another question, sir. Is end of inflation and the supersymmetry breaking scale same or not? So is the end of the inflation or supersymmetry breaking scale same or not?
There is no definite answer for this. It depends where is the scale of supersymmetry breaking. If in the real world, if there is supersymmetry at low energies, then yes, at the end of deflation there should be a breaking of supersymmetry. It may be that this is not the case because experimentally we don't have an education right now of this. In which case supersymmetry would be only needed, is only an ingredient of the high energy theory. With my proposal could be related directly to inflation, but all superparticles would be very heavy.
So thank you, sir. So is the problem of afflating the inflationary potential from ADS to DS space solved or not?
No, it is not solved.
So thank you, sir. We have another questions. Can you say inflation is a stabilized Kahler moduli?
In order to talk about inflation, necessarily one has to address the problem of stabilization, either with assumptions or with more specific proposals about the stabilization mechanism. So yes, they are related.
Yes, sir. So thank you. We have. So what is the microscopic origin or region for inflation in string and M theory?
Well, this question is related to the realization of inflation string theory, which I described it in my talk.
Yeah. Thank you. So thank you. So this may be the last question, sir. So can we say inflation is an effect of brain wrapping in different cycle of Calabi
It is, sorry? Can you?
So can we say inflation is an effect of brain wrapping in different cycles of Calabi manifold?
Could be. There are models that they use the wrapping, but I don't think we can say that there is a direct connection with this.
So thank you, sir. As there is no more questions, so we can conclude our discussion session, sir. So thank you very much for your nice presentation and your wonderful discussion session, sir. We would like to say thanks on the behalf of the Department of Physics, Pabna University of Science and Technology, sir. We are so grateful to you that you have accepted our invitation in this corona pandemic situation, sir. And the main aim of our program is to motivate and encourage our students in this corona pandemic situation. So thanks again for accepting our invitation. So hopefully in near future we'll arrange another webinar with you if you have a time, sir. And after pandemic, I'll definitely invite you in my university for face-to-face session for my student.
Thank you very much.
So thanks for today. So bye for today, and thanks again.
Thank you.
Hopefully see you again very soon.
Bye.
Bye.